right, real quick, high level on material properties. The material comes out pretty much on par with other laser powder bed systems that I would say are running very well. The mechanical properties are very similar or better than as cast material. Comes out fully dense. And the geometric accuracy, kind of the rough rule we use is it's accurate within plus or minus 50 microns, or that's 0.002 roughly, plus 0.2%. So larger, the error of accuracy scales with the dimension that you're measuring. For specific mechanical properties, we have full data sheets on Inconel 718 and TIE 64. We'll be releasing aluminum shortly, and both of these data sheets will explain all the strength and elongation in detail with different heat treatments, and they're both available on our website. Okay, so let's get into some of the dimensional limits of the system. Kind of, again, I want to kind of sort of bookend what the dimensional limits and what the angle rules are for this system, so that we can get into more detailed conversation of selecting parts. So for thin features, the minimum thickness of a pin is about 130 microns. Minimum thickness for a wall that is being fluid tight and non-porous is about 150 microns. And both of these behave similarly in that the minimum achievable thickness is a function of angle. And so because of the layered nature of the process, at 90 degrees, remember this is vertical, for a pin it's about 130 microns, but as the angle goes down, it approaches horizontal, the minimum achievable thickness is a bit larger. It's up more towards 190 or 200 microns. Same thing for the walls, although the dimensions are slightly different. So as I mentioned before, we're able to achieve more intricate geometries, control them more precisely and more continuously as a function of the advanced process control and application that we have, but also as the recoder, like I mentioned. And so structures like these thin pins are extremely delicate, and with conventional systems, once they reach a certain aspect ratio, the subtle force of the recoat mechanism is too much, and it starts to push them over. With the VELO system, if you wanted to print minimum thickness, 130 microns, you can print it the full height without any distortion, meaning you can print it 400 millimeters tall if you wanted to. So you've got the freedom that others don't when it comes to these thin pins. Thin walls, similar case here, though they have rigidity in some orientations, but with other systems, you're limited to the orientations that you can do. And so this radial heat exchanger type geometry is showing that the walls have uniform thickness and they're not being distorted regardless of its orientation relative to the recoder, because there is no interaction, again, between the part and the recoder. I'm going to plug in a kind of a real customer example here relative to the thin structures. This part is a oil to water heat exchanger from a company called PWR. PWR manufactures really advanced heat exchangers for things like motorsports and aerospace, stuff like this. And to give you a little bit of scale, the part is about 3.5 inches cubed total, and the thinnest walls you're seeing on the inside here, they're about 250 microns. What PWR did is they went around to all the major laser powder bed manufacturers and tasked them with trying to print both this very thin, difficult geometry, but also doing it with a high level of consistency of being leak-free, because obviously you can't have mixture of fluids in an application like this. And because of our process control and because of our unique hardware, namely the recoder, we were able to print this part, print it well, print it consistently, and PWR decided to settle with VELO Sapphire as their solution. Okay, let's talk about closures in general. So I'll break it up into a few cases, but I'll talk about first horizontal holes. So this is any kind of small orifice or flow path that you have flowing through a part, or a large tubular diameter like this. The maximum ID we can print today is roughly 40 millimeters. And when I mean print without supports, without having to add supports. And the minimum size of a horizontal hole or port is about 500 microns. If you change the tilt angle of the part slightly I mean say about 10 degrees or more off of horizontal, then the maximum ID increases dramatically, right? So you can print, instead of 40 millimeters, you can print 100 millimeters or more ID of a tilted port or hole. kind of working off that, dome closures behave similarly to, let's say, about a tilted tube, a large tilted tube, in that we can print a closure. And it doesn't have to be perfectly round. What I mean is, as long as it's constrained similarly. So if you look at this turbo volute example, you have a round-ish geometry. As long as the radius or the diameter of curvature isn't much more than about 100 millimeters, you can print it without supports. This example here is perfect to show that if you can imagine applying supports in here, okay, not such a big deal, but to get the supports out of a volume like this is extremely difficult. And so it's really valuable for large manifolds, anything with a large internal closure, to be able to print those without supports. Horizontal spans. So if you do have something that goes below some of our minimum angle thresholds that I'll get into following these slides, we can print a maximum span of about 10 millimeters and a minimum span between two vertical walls of about 200 microns. This rule is expanding a bit today. We're working on some other processes, and I'll get into those a little bit later. These are the rules as it stands today.